Welcome to this presentation, this video about database modeling. This is just a short introduction to how to make database models and why we do it. And I will give you a short introduction to data types, relations, entities, and all that stuff you need to know when you begin model databases. So this will be about data and databases. What is data and what is databases? I'll talk about normalization of data. That's how we structure data. I'll talk about data types. That means how we can identify which data should have one type, for example a number, and which one should be a string. Then I'll talk about relations, how we can relate data to each other. That means entities to each other. And then I will conclude this presentation by showing how to make diagrams, entity relationship diagrams, in a tool called MySQL Workbench. So data is everywhere. We see data everywhere, but perhaps we don't see them, but we know they are here. And we have complex systems which can handle all these data, so we don't have to go and figure it all out. That's what we use computers for. So let's have a look at some basic data. We have this male. He's 183 centimeters long. He was born in 1969 in a small town called Ringsted, and he's married. This could be some data about this guy. We could have many others, and this is a woman. And this woman, she wants to do taekwondo. She's self-employed. Her name is Nana, and she's 1.72 meters high. This is a music store or a record store. In this record store, you will perhaps not notice that there are a lot of data here, but they are. Data everywhere. There are data about the albums, where they are stored, who's playing, how long are the numbers, and all that stuff. And if we go to a modern record store like iTunes, you will see there's data everywhere. Here we have some songs from an album. How long time is the number? What's the price of it? Yeah, you can see there's a lot of different kind of data in here. If we have a closer look on this this record, we could perhaps store or save all the data we need in our database, and we could store perhaps more than we need. But the first thing we do when we begin to design a database and make models of a database is to find out what's important. And in this case, it could be the album title that was important. Perhaps we want to record that or have to save that the temperature of the release day was important, but I think that was just be trivia in, for example, a Wikipedia page. The guy's favorite pet, I don't care. So I think that will not go into a database about the records. Year of release will be quite important because we know we have to be able to search for albums for a particular year, and the number of albums sold could be important if we want to find out if this has to have an award or something like that. The producer would also be interesting to know, and the number of songs, of course, would be interesting, and many other stuff could be interesting, but not all data is important, as you can see by this example. Before we go into the database modeling, I will just cast a few words about this stage: data, information, knowledge, and wisdom. Because some people interchange information with data and knowledge with information. So I'll just clear it out here with a small example of what is data actually. Data could be a number, for example 183. 183 could be the height of a person. It could be seconds. We don't know. We haven't qualified this number yet. When we qualify it, when we put it into a context, it becomes information. But right now, it's only data. Like these 5 letters, which gives the name, Nils. But it could be anything. This could be short for something. It don't have to be a name. We don't know if it's a name. We can only recognize this as a string, as a text. So information could be the name is Nils. Now we put Nils in a context. We put the words, the 5 letters, we put them into a context. So now it gives more meaning. That means that every time we step up on this ladder, you can say, you will notice that we give them a certain kind of quality or context. We give them some more than they had before. So name is Nils. Yeah, that could be information. And then we have knowledge. Knowledge could be, I know how to make Nils happy. This is a more complex way of handling information because there could be different ways. They have to make a decision or have to make an evaluation of what could be the best way to make this guy happy. And then we have on the top of this ladder, we have wisdom. And wisdom could be some kind of advice. It comes from perhaps many sources of knowledge. So when we talk about data, data is really the basic building blocks of our information, our knowledge, and our wisdom. So we'll go back to data modeling again. So we organize data in databases, and they are everywhere because everything is connected now these days through the internet, and the internet is one large database. So this is the symbol of database, if just in case you should see it somewhere else or use it when you want to make diagrams. This is the symbol of a database. And for example, if we take this record store, we had all these pieces of data and we like to put them into a database, but we cannot just put them in. We have to make a kind of structure. That's why we use a model. And a model can be seen as a model of the reality we want to mimic into our system. That means we have to exclude something and include some other thing. Like I said before, not all data is relevant. We have to make a choice what to put into this database. So I will make a short example. I will use the example of students in this presentation. For example, I have these 5 students: Anne, Bill, Charlie, Donald, and Eddie, and they are enrolled in 3 different classes. 3 of them in the same class, class Q, and then Charlie is in P and Donald is in S. And they have some contact info, and somehow this could be data from a spreadsheet or a list of students. But we want to put them into a database. There are some rules we have to follow. And those rules have a name. It's called normalization of data. That means we try to make our data more clean. That means we clean up the data, we clean up how they are structured, and we ensure a proper structure so it's easier for us to get consistent data. That means data which we can trust, which we know have the same form. Like before, you saw that the female had a height 1.72 meters, whereas the male had has this height of 183 centimeters. So we have to have the same units. We have to, otherwise it's not easy to find out, for example, who has this height above 180 centimeters if half of the persons in the database are stored as in meters. So we have to be aware of how we store our data or how we structure the data. So that gives us data consistency. That makes it easier to to retrieve data and input the data. It gives us better chances to search for data properly, and it increases the quality of the data. That means they are more reliable. We can trust the data. So that's the purpose of normalization, and perhaps you can find many more. But that's those three key issues I have chosen for this presentation. In normalization, we have what is called normal forms. It's invented by a guy called Card. And this is the first normal form I will show you. In this presentation, I will only use the first three normal forms, and usually when I design my database, I use these three, at least two. And in the traditional database design theory, you can have more than 6 normal forms, but they are more theoretical, in my opinion. So first normal form, it's about only one of each in each column. And column is, for example, the name or the contact info. So only one of each. And one of each I will explain you in a moment and give you an example. But one of each means we don't mix up many information or many data in one column. For example, if I have a list of students and they have different kind of interests, then perhaps one guy will have 2 kind of interests and another one will have 5 kind of interests. So this will make it make it variable in this column called interest. So we have to clean it up so there's only one interest, for example, or one reference to another list of interests. So I will show you an example in a moment, a simple example of how to handle one of each. And then we have to have a unique identification of each row, because we index our data in the database, and we have to have this index so we can search the data fast. And if we go back to our students with these data we have, you will see that this over here contains more than one of each. It contains the address, the zip code, and the city. So I would recommend that it would be split up so it's easier to search for example, which students do we have in Aalborg with the zip code 9000, or who lives in Vestergade in Aarhus, for example. And then we have more than one of each in this contact info. And then again, we have also no unique identification. We don't have, for example, usually we use for people, we have this ID. This could be the social security number or something else. But we used to have some kind of ID, and a name is not enough. When we combine the name with the class and with the contact info, perhaps it will be enough. But there's an easier way to do it. The easiest way to do it is to make a new column and name it, for example, ID. And then let the database give the next available number to you. That means the first one will of course have number 1, 2, 3, 4, 5, and if we delete Charlie, number 3, and we try to append another one, the database will automatically give the next one the ID 6. So there will be no duplicates. And that's very important, because if there are duplicates, then the index will fail and the database will struggle to find the correct person. The ID column, and the ID column is also what is called a primary key, because the database needs to have an index of all the rows, and that's why we have this unique identification. And this index is called the primary key. We always have to have a primary key in our database, in our tables. And now here we have split up the contact info into 3 columns. So now we don't have one of each. The rule one of each is complied now, because we have now, for example, the zip in the zip code in one column and the city in one column. That means we can search for all those with a zip code of 9,000, and we can sort, for example, our rows here ascending. So that means Aalborg will come before Aarhus. The second normal form is about how to remove redundancy or repetition of data in the rows. And we need to do that because then we have a more efficient data structure, and it makes it also easier to make changes to the data. For example, in this case, we have MDU 12Q2 as they are repeated. The data is repeated in the class column, and that means we want to change the 12Q2. For example, if we misspelled it or something like that, then we have to go over all the rows and change them separately. So it would be more convenient and more secure quality-wise to put it into a different table and then, or different entity, and then reference this class. And I'll show you in a moment how it's done. And then we have over here the zip and the city. Also, we have a lot of redundancy here. 8,000 goes through all the 4 of the rows. And we have, for example, it could be that we have a database of 500 students, and many of them come from Aalborg. That means we have to carry on with a lot of repeated data and redundant data. You may notice that in the address column, we have also some redundancy here. And in theory, we could normalize this column as well. But in practice, I tend never to do it. But you could do it by making a new entity for the addresses. So let's have a look at how it's done. This is an entity. This is the student's entity, and the student's entity is described through the attributes. That means the ID, class, name, address, zip, and city together forms the entity students. And then we could make, and we will in this case, make another entity called classes. And in this goes only the class name, which you saw before in the students entity, the class column. So we can have these two entities beside each other, and then we need to relate them to each other. And we do that by making a class ID in the students entity. And then we can make the relation like this. Now these are related by the ID in classes and the class ID in students. This is what we call a foreign key in the students entity now, because it's away from home, you can say. And then you have in the classes, you have the primary key. As we have in the students, we also have an ID there. So we need to have a foreign key and a primary key to make a relation between two entities. We also describe the relation in terms of what is called cardinality. I will come back to cardinality in a moment, but in this case, we say that many students can be in one class. Or, as a rule of thumb, if I just need to conclude this about the foreign key is on the many side, and the primary key is on the one side. So, one class can have many students, and one student can only be in one class. By that we mean that a class can have a lot of students, for example 30 students, but in this design one student can only go into one class. So that's how we describe it here, that many students can go into one class and one class can have many students. If we need to make another symbol instead of many and one, writing it in letters, we use this this notation called crossfoot. And crossfoot is symbolized with this this triangle, this crossfoot on the left side. That means the many side would be this crossfoot, and the one side will be just a line symbolizing 1. We have a few other notation. I will show you one in a moment that we can use instead. This is called Chen notation, named after a guy called Peter Chen. And in this case, we use those entities, boxes, and they are related to each other. And in between this relation, or what is describing the relation, is a text in a square. For example, this can be read as students are in class, or class contains students if you want to read it from the right side to the left side. And in the Chen notation, we symbolize attributes by these kind of balloons, or these circles, where we can say that, okay, now we have a few attributes for our entities. And to describe the cardinality, as I said before, we use the M for many and the number 1 for 1. And cardinality is what is the relationship. It describes, is this many to 1? Is it 1 to many? Is it many to many? Or is it 1 to 1? This is what we call cardinality. And in the Chen notation, you can see the cardinality by this this square and then the two symbols on each side. Let's go back to this example from before. I will continue with the crossfoot. I think it's more readable, but that's only my opinion. And we have this student and we have the classes. Let's see how it's working when we want to replace the values in the student's entity with the new values from our class entity. So the first thing we need is, of course, the class entity. And now here we have populated with some values, put in some values, which is these 3 classes we have from the student's class, student's entity, and it's Q, P, and S. And as you can see up here, we now need to, in the student's entity, to change the class to class ID. And then we have to reference, instead of MDU12Q2, we need to reference ID number 1. So it would be 1 here, and it will be 1 here, and in the next one it will be 2. And S will be number 3, and Q is number 1. So now we have a reference to another entity. Instead of MDU12Q2, we have now 1 in the class ID column. And that means if we want to change the name of the class, we only go to the class entity and change the name. And then when we have a list of our students, it will make a lookup in this class entity to see what does 1 mean, what does 2 mean, and then it will insert MDU12Q2 instead of 1 when we see it in our screen. The third normal form is about how to remove these columns that are not direct dependent on the primary key, and this can be quite difficult to understand at the moment, but in a few moments you will understand it much better when you see this example. And in this case, the primary key, of course, is the unique ID, as I said before. So here we have some candidates for the third normal form. This would be the zip code and the city. As you can see, we have kind of a key here. It's the zip code, which has a relation to the city. That means 8,000 goes into Aarhus C, 9,000 Aalborg. So these are related to each other, and the city column is thus not related directly to the ID column. And that's why we are able to remove the city column and then reference with the zip instead to a new entity. As I will show you here, we can make this entity called zip city. And in zip city, we have, instead of ID as the primary key, we have zip. And in the in the students, we can now remove the city column because we can reference to this zip city entity instead, this one. So now we can make a lookup instead of typing this Aarhus City each time when we create a student with the zip code 8000. We just reference 8000 and then the database will make the lookup for us and then get the data for us when we have to display them. Data types are quite important when we are making a database design. When we make data models, we are not obligated to put data types in it because we only care about how are these entities related to each other. We make what is called an entity relationship diagram or model. But when we want to get closer to the database, we need also to put in the data types. And why do we do that then? Well, here's the most important data types, which I'll just give you a short example of, and then I will show you in the tables how they can look. So here we have the data type integer. Integer is spelled int, and a typical integer would be 42. Then we have, for example, the decimal. The decimal data type is a floating point number, that means decimal number. It could be 42.1. The date time is also an important one. The date time data type puts date and time in one data type. That means 12/24/2013 and then 18:59:59 seconds goes into one field or one piece of data. And then we can have, for example, the varchar, and there are many more. I can't remember how many there are, but there are lots of data types. Integer, for example, comes into tiny integer, small integer, big integer. Varchar is a variable char, that means a variable text. And you have to, when we use the varchar, as I will show you later on when we use a tool for the database design, we have to identify how many chars, how many characters do we need for this string or this text. And an example of that could be a name, or it could be a text, or it could be a city, a name of the city. So these 4 data types are those that are used a lot in databases. Then you have many others that you may come in very handy sometimes. But these you will know by heart, I'm sure, because as you will see in a moment, I will use the 2 of them most. In this case, we have, for example, this short, simple diagram. We have our students, we have our classes, we have our zip city entity. And if we want to put some data types on each of the attributes, we need to do that because the database needs it in order to make it more efficient and in order to make relations work properly. So for the students entity, we put in these data types, and I will explain them in a moment. And for the classes, these data types, and the zip city, these data types. And then we have the relationships again. As you can see, we have all the IDs will always be integers. And that's because it's a very efficient very efficient data type for the database to handle. It is easy to calculate on integers. And then when we make relations, for example, in this case, the class ID, we reference or we make a relation to the classes entity. It needs to have the same data type as the reference table. That means class ID and ID in the classes has to have the same data type, in this case integer. The name will be a string or text, and I have made a limit of 100 characters, and the same goes for the address, and the zip code can be an integer. If it's possible for you to use an integer, then do it, because integer is shorter in the memory on the disk. It takes up less space than the varchar. And over here, we have, of course, our integer in the classes. Like before, the student's ID will also be an integer. And the class, the name of the class, will be a short text, 20 characters maximum. And here we have, again, it's an ID, or it's a unique ID, so therefore we have it as an integer. And then the last one is the city, which would be a variable, a varchar, with a limit of 100 characters. Now we have seen how a relation is done, how it's two entities are related to each other. Let's have a look at the types of relations. And this is a typical one-to-many relation. Actually, it's a many-to-one, but it doesn't matter. I could have put the class's entity on the left side of the students, and then it would be a one-to-many. But it's the same, many-to-one or one-to-many. It depends how you read it. And in this case, we need to have, when we have a one-to-many, we need to have a primary key that is in the classes, the ID column, and then we need to have a foreign key in the students entity, and in this case it's the class ID. And then we have the many-to-many relationship, and many-to-many is it is possible to make a many-to-many relationship in the ER diagram, that's the entity relationship model, but it's not possible to have it in the design, as I will show you in a moment. So we can, in the model, make a many-to-many relation. For example, in this case, many students can go into many classes, or if you will call it courses instead of classes. For example, if we have elective courses, then a student can choose perhaps 4 elective studies or classes. So that means that the students will mix across the classes, and therefore a student can have, for example, 4 classes, and the classes can of course have many different students. So in this case, and we see this a lot in database design, we have a many-to-many relation. So we can also have a one-to-one relation, but I tend never to use it, because a one-to-one relation could or should be replaced by an attribute in the entity. So let's see how we come from database model to database design. The first thing we do is that we create foreign keys. That means we find out that now these two are related to each other. That means we need to have a foreign key on the many side. And then we of course put in some data types. And then we take these many-to-many relations and resolve them into intermediate tables. And I will show this in a moment. And creating foreign keys, we have seen that in the previous slides. And we have just had a look at the data types. So let's have a look at how to make intermediate tables. Let's say we have this case that the students can select among different kind of classes. So a student can participate in, for example, 3 classes, and a class can have different students. So that means we have a many-to-many relation. And we resolve this many-to-many relation into an intermediate table by putting in an entity between them, or a table in between them, with a primary key and 2 foreign keys. In theory, we don't need the primary key the ID in the student underscore classes, but I tend to do it all the time anyway, because there are some side effects that it can make the database run faster. And then we can make the relation between the students and the classes through this intermediate table. And we do it with saying one student can participate in many classes, and one class can have many students. So now we have a relation between the students and the student underscore classes through the primary key in students and the foreign key in student underscore classes. And the same goes for classes. It relates the ID from classes to class underscore ID in student underscore classes. So let's have a look at how it could look when we put in some data. Let's say we have 3 students. We have Anna, Ben, and Charlie. They have the ID 1, 2, 3. And then we have some classes or elective studies. It's PHP, JavaScript, SQL, and jQuery. And they have the ID 1, 2, 3, 4. And then we want to mix it up. So Anna wants to participate in the PHP, and Anna wants also to participate in JavaScript, and Ben wants to participate in JavaScript and in jQuery, and Charlie wants to participate in PHP and in SQL. And you can see this through this, that if we replace the IDs from students and from classes, we will have a list like this, that Anna goes into JavaScript, Ben JavaScript, Ben jQuery, Charlie PHP, and the last one Charlie SQL, because Charlie has number 3 and SQL has number 3, like this. So when we make a query or we want to select some data through this many-to-many relationship in the database, we will get a list that looks like this, because the database can make the lookup in the tables, in the related tables. So it replaces one with Anna and one with PHP, for example. So let's have a look at how we can do it in MySQL Workbench then. MySQL Workbench, or MySQL Workbench, is an open source application that you can download from this URL, mysql.com/products/workbench, or you can just Google MySQL Workbench. And MySQL Workbench is a tool that you can use to visualize your database and use for modeling and making a database design. So I will make a database design of this very simple database, this structure that I've been working in this presentation. So I have downloaded it and installed it, and I will create a new EER, entity relation model, and I will add this diagram, and in here I will make this first table by clicking on this icon, and this table I will name students. The first column I will make is of course the ID, and it will be the data type integer. It will be the primary key. It will not have any null. That means there has to be a value in this this row or this column. In each row there has to be a value. And then I would like to make it auto incremental. That means that it will the database will automatically fill in this ID with the next available number. That means I don't have to take care of if the row is unique or not, because it will always be, since the database will give me the next available number. And then I need to have a name for this this student, and the name would be of a varchar of let's say 100, and then I would like to have an address, and again varchar 100, and then I would like to have a zip code, and it will be an integer. In this example, I will make it possible that a student can participate in many classes. That means I have to have a many-to-many relation between students and classes, and therefore I don't have a foreign key of the class for the student here, because that limits the student to only participate in one class. So this is my student entity, and then I need to have the classes. So I will make an entity called classes, and again I use an ID as the first column with auto incremental, and then it has to have a class name like this, and I think it's okay with 20 for this varchar. I have to resolve this many-to-many relation between the students and the classes. In order to do that, I make another entity that will go in between these two entities, and if I will name it students classes. And as you saw before in the presentation, we need to have, of course, an ID, which will be also incremental, and then we need to have a foreign key from the students. That means student ID, which will be an integer, so it resembles this one, has to match the primary key for the students. And then I will have a class ID, which also will be an integer, because this is also an integer up here. When I want to relate these entities to each other, I double-click this entity which holds the foreign keys, and then I go to the foreign keys tab down here, and then I create a new foreign key. That means I don't create a new foreign key, but I create a relation between two entities through this foreign key. I do it like this. I choose student, and then I will write student underscore classes. That means this table will be related to this table, and I want to reference this one over here, this students table. So I choose the reference table students, and I want to use this foreign key student ID and reference it with the ID of the student. So in this drop down, all the columns from the reference table or entity students will come up here, and automatically it will try to find one which matches the data type. In this case, it's the ID. So now I have my relation, and when I hover this, I can see that these two are now related, and in here I have this red square which signals that this is now a foreign key. As you can see down here, this is not a foreign key right now, it's only an attribute. So I need to make another foreign key, another relation to this one over here. So I will make a similar one which goes from classes to students classes. And it doesn't matter what you write here, except that write something that is understandable. And I would like to reference the classes table. And to do that, I will use the class ID as my foreign key, and then I will find the primary key from the classes over here, which of course will be the ID. So now I have my relations between these, and as you can see, it reacts when I drag them around, so I can make my layout as I wish. So now I have this relation which goes from class ID to classes, the primary key of classes, namely the ID. And here it goes from the ID of the students to the student ID, foreign key in students classes. So now they are connected with each other. Now we need to make another entity for the zip code, this zip city. So I will make another table here. I will name it zip city, and then I would like to give it the ID and auto incremental, and then it will be city as I can look up in this table. So it would be 100 for my varchar, and then I have to relate these two to each other. And as you can see, now my ID, oh, it should not be ID, it should be zip actually. So now they are related. These two will now be related in that manner that this one over here, this zip code in my students, will be my foreign key. And this one is of course a primary key. I can see that because it has this yellow key in front of it. So I will go to my students, and then I will create a foreign key for this relation. And this would be zip city to students, and I will use the zip city as reference table, and I will use the zip in the students, the zip column in the students as my foreign key, and then I will reference this zip column in the zip city table. So now I have my structure for my small database of students. As you can see, there are some symbols here that perhaps you haven't seen before. I mean this one here. I have this line here, and I have two lines here, and these lines symbols that that they are mandatory in participation in this relation. And what we are talking about here is participation of entities. And participation can be understood like this. We may have a zip code, and we may have a city which will never be used by students. We may have students that lives in one town, and perhaps we have 170 city entries in this table. So this zip city is, by that means, optional in the relation. That means it can live without a student. We can have a city inside this table which will never be used, but a student cannot be created without having a zip code. That means the student has to live somewhere. So the student, in this relation, is mandatory, but the zip city will be optional. And we can edit the relation by double-clicking the relation, and then we can go to the foreign key, and then we can say that here we have this mandatory checkbox for both tables, and as I said before, this one is not mandatory. So when I click this or deselect this, you'll see there's now a circle instead of the line. That means that this is now optional. It doesn't have to be not all of these entries has to be found over here in the students, whereas these students, they all need to have one entry here that can be found over here. So the student cannot live without a city, but the city can live without students. And the same goes perhaps for the classes, that we can have a class without any students. We could have this situation where we begin the year with creating some courses, some classes, but none of the students will sign up for it. So we will have this empty class, and that means that a class, again, as the city, can live without any students in it. But the students, and thereas the student classes, cannot live without a class ID, a class name. So this one will of course be optional again on this side, on the classes side, but it always have to be here. Perhaps we have this rule that students can participate or enroll for a study without being in any classes, but I don't think that would be the actual situation. Therefore, the student here will always have this mandatory relationship. That means the student has to sign up for a class. This is what it means when we decide that this is now mandatory, this relation, as you can see here. The student is mandatory into this relation for a class, but the class can exist without any students participating in this course. And the city can exist without any students, but the students cannot exist without having a city to live in. So let's just sum it up about data modeling, database design. We have normalization as one of the primary processes. And normalization, we want to clean up data. We want to ensure proper structure. And that means we get data consistency, hopefully. And then we enhance the search for data. And we increase the quality of data. That means that we can trust the data we put into the database. They are reliable. When we normalize, we use the 3 normal forms. First normal form is about only one of each in each column, like we did when we took the contact info and split it up into 3 columns. Instead of contact info, we now have address, we have zip, and we have city. And then we put in unique identification of each row. That means we put in an ID, which would be typically an auto-incremental number that the database gives us, so we don't have to take care of this uniqueness of the rows. Then we have the second normal form. It's about how we remove redundancy, repetition of data in rows, like we did when we have these class names. We put it into an entity called classes, and then instead of have the name of the class in each row, we put in the ID of the related row in the entity of our classes. Then we have the third normal form, which is about how we remove columns that are not direct dependent on the primary key. And in this case, we use the city. We put that into a new table or new entity called zip city. So the city is related by the zip code to each of the students. And we have a look at how different kind of relations. One of them is one-to-many or many-to-one in this case. And we use a primary key in the one side, and we use a foreign key on the many side to relate these two entities with each other. Then we have the many-to-many relations. In this case, we have the students that can go into many classes. So we can have many students mixed in many classes, and to handle this, we go from modeling to design. And in this case, when we have a many-to-many relation, we split this relation into or we create an intermediate table between the two tables. When we go from modeling to design, we create foreign keys, and we of course enter some data types. In this case, in this presentation, I showed you 4 kind of data types, typical data types, very used. It's an integer, the decimal, the varchar, time. And as I said before, when we go from modeling to design, we always need to have a look at the many-to-many relation. How can we resolve them into intermediate tables? That was all for now for this introduction to data modeling and database design.